So you can see instead, when we take the inverse, the x-axis is normally pi over 2, pi over 4, all of that. But now when we do the inverse, the y-axis is all the pi over 2, pi over 4, all of that. So basically the x and the y just flip, right? So looking at this example, that is a function, the restricted domain here is negative pi over 2 to pi over 2. And this will just be a common one. I mean, again, like I said, you could restrict it differently, but as long as it's not, as long as its inverse will pass the vertical line test, which means the trig function will pass the horizontal line test, then it's good to go. And the range is still negative 1 to 1. So now looking at how the heck do I get, domain and range here? Well, my domain of my inverse is negative 1 to 1. It's my range from my original. And my domain of my original is the range of my inverse, right? And now there's, just like so many things in math, there are two different ways, at least only two for now, two different ways that we will write this function. So the inverse of y equals sine x, it will either be written as, traditionally, I think we will write it as y equals sine, like sine to the negative 1 of x, right? Or you'll see sometimes, maybe in ALEKS, I'm not entirely sure, but it's arc sine. Arc is meaning inverse in this case. And if people don't like that negative 1, or sometimes it can be confusing, arc sine, arc cosine, arc tangent, like these represent inverse. I think on some calculators, they might even like say this instead of confusing you and making because sometimes people think, oh, sine negative 1, is this 1 over sine? But that's not what it is. That's what cosecant is, but it's not 1 over sine. It's the inverse, right? Okay, so let's do some examples of calculus, and then we'll look at graphs
for that. I just want to say they have a different button for representing the reciprocal, which is x to the negative 1.
Okay. So I didn't realize they have another button for that. Yeah.
Yeah.
Okay.
It's like, to the negative 1 power is the same as, but yeah, isn't that what that means?
Yeah. No, it is. It is. So to the negative 1, it means that, but in this case, this negative 1 does not mean so in order to get arc sine, right? It doesn't mean 1 over sine. It's actually taking an inverse.
It means something completely different.
Yeah, it means something just freaky different. Yeah. We're just, it's a little too maybe crazy to think about, but yes. So we just want to make sure we keep our things straight here. And so if you're not a fan of that negative 1, feel free to write arc. If you're writing work and you aren't confident with it's confusing, feel free to write arc in front of it, and then I know that's the inverse. So they're giving us some quote unquote easy ones to start with, right? So what I want to do here, we're trying to figure out inverse sine, arc sine of negative 1/2. And so this is my ratio from, it's my, on my unit circle, it's my y because I'm looking at sine. And the answer here is going to be an angle. So what I'm trying to figure out is at what angle does y, which is sine, equal negative 1/2? So I know if I think of just this first quadrant, right, 0 to pi over 2, and you can do degrees or radians. I'm going to do radians because I like that. But if you want to do degrees, feel free. It's not specifying here. And this would be negative pi over 2 or 3 pi over 2. I think, we'll figure out what we want here. This is pi.
You said at what angle does sine equal -1/2? Is that what that kind
Yes,
of?
yes. At what angle does sine equal -1/2? And now here's something kind of crazy. There are like infinitely many answers to this.
Mhm.
However, typically we look for answers between at this restricted domain. So between
Right. Okay.
-pi/2 and pi/2, which is also why I shouldn't even really include this piece or like this. I should just say, yeah, we're looking -pi/2 to pi/2 typically. And I'll usually tell you, right? So I'll usually tell you. So here I know -1/2, that means the y is negative. So it's somewhere down here. And I know it's either going to be like -pi/3 or pi/6. I just have to figure out which one it is. And oh, Jakob said in the chat, he thinks -pi/6. So I'm gonna say I'm pretty sure that is correct. This is not really a great drawing, but so at this point, if this is like just pi/6, um, this would be the point value there, and there's my sign. So now I know my angle is -pi/6. Now we're used to looking like we're not even considering this side because we're considering only between -pi/2 to pi/2, right? In our restricted domain. And we're not really used to that. We're used to like 0 to pi or 0 to pi/2, but it's not so bad because anything in this first quadrant, basically the reciprocal is going to be here, and you can figure out like if you didn't know which one was 1/2, but you knew pi/6 was 1/2, well, you just flip it and make it negative to make it negative, right? So the nice thing is this is kind of nice when solving these types of okay, so now let's try part B. So I have arc sine now of √3/2 is what angle? Remember, what angle when I take sine gives me √3/2, and I want positive. So now I kind of know right away. Ignore here, 0, pi/2, -pi/2. I want positive √3/2. So, and I want sine. So it's not the 60 or 60. It's not the pi/6, which is 30. It's going to be this pi/3, and I get 1/2 √3/2, and it should be pi/3. And again, these are angles that you know. So this is like just to show you how this works. Eventually, there are going to be problems where you put this in a calculator and you get a decimal and you round, But it also is important to know these angles that we've worked with for so long, right? Now, maybe this last one, they're trying to make it like, I mean, not difficult, I guess, but trying to just trip us up a little. So we have 5 pi/4. So if I have, so in this case, this to me looks like an angle, right? This looks like an angle. I mean, it's they're not meaning for it to be, but this, if I calculate like what is 5 pi/4 in a calculator, because I want, this is a case where you'd put this in a calculator because I don't know what angle gets me when I take sine gets me 5 pi/4. I don't know. This doesn't make sense. So this is approximately like 4, I think. It's like 4-ish point something. But looking up at our inverse sine at our function up here, looking up at this, my domain and range, my domain is -1, right? And approximately 4 does not fall in my domain. So this is not going to work. And so what we're going to say, so I'm going to say not in domain of inverse sine of x, right? And the domain is -1 to 1, right? Because this is 4, that's outside of this. And another thing is we do not take arc sine or inverse sine of angles. You take inverse sine of a number -1 of a, of either a pi or 36, or well, no, I'm lying. Either 1/2 √3/2, like √2/2, those numbers that we know, or of decimals, like 0.85, 0.23, 0.05, something like that. That's what we take inverse trig functions of. So in this case, our final answer is just that it's undefined. Now, if you were really curious too, or if you were stuck, throw that in your calculator. It's going to be pretty mad at you. It's going to be like, this is totally wrong. And like, what are you, like, error everywhere. Right. So that's good. I mean, that makes the problem kind of easy for you, right? You can just move on. Okay. So now we're going to take a look at the other. So this was sine. Now we're going to dive a little bit into cosine and look at tangent, because, these are our main three guys: sine, cosine, and tangent. And then hopefully we'll, see some good examples after we see each type of trig function. Sorry, there's a question. For y equals sine x, the domain will always be -π/2. Yeah, so unless otherwise noted, and this is a good question, Veronica, unless I say otherwise or the book says or something, we're going to assume I highlighted so much here, but we're going to assume that of inverse sine, the domain and range is this, right? Or of, it's these two, it's related to these, right? Sorry, off topic. Is all homework due at midnight now? Did I say, I did extend the homework. Did I make it? I have no idea, honestly. I've changed so many homework assignments just for both my classes. Does anyone know what time the homework is due? Oh, it was at 6. Okay. So sorry. It was due at 6. I can extend it. If people, were all 3 of them were probably due at 6, right? Yeah. Oh, you see 12 p.m. Okay. Well, I may have, so Alex is 6. Oh, yeah. So in Alex, they were due at 6, but the book problems I made due at midnight. If that makes sense.
I think the book problems are due on Thursday, I think.
I pushed them to Thursday. Sure. And who knows? I don't remember what I did, but yeah, but if you see, like, well, 12 p.m. is noon, but if you see like midnight for you, maybe we exchanged emails and I changed it for you. I don't know. But I can just shoot me an email, those of you that need anything, and I can try to extend it. Yeah. Okay. So 6.1 book problems were due today. Someone's saying 6.2 and 3 were due Thursday, or are due Thursday. Yeah. Okay. All right. Hopefully that we can, and at the end of class, like I said, hopefully I have time to go over the quiz and answer all these questions and update anyone's homework or whatever we have to do. Right. Okay. So yes, we will always use the -π/2 to π/2. Okay. Now for cosine, so we run into this like nearly exact same issue, right? I mean, if I did a horizontal line test here, like this is not going to be so nice, right? So I'm going to pick. Now, in this case, I'm not going to do -π/2 to π/2 because look, that gives me, and again, it would pass the line test. So I'm actually going to pick 0 from 0 to pi for cosine. So although sine and cosine look very similar, the domains are going to be slightly different for our inverses, the domains we choose, right? So this point is 0, 1. This point is pi -1, right? And this point is 0 pi/2. Or wait, I flip-flop that. So ignore everything I said. Pi/2, 0. Okay. So we are going to pick this piece in here. Oh, it's not liking me. And we are going to invert this. This is going to be our cosine, y equals cosine x. So the restricted domain is going to be 0 to pi, and the range -1 to 1, right? That it stays the same for both. And then remember, we just swap this, swap that there. So we get -1 to 1 for our domain and 0 to pi for our range. And so if we graph this, maybe make this -1 here, make this 1. Maybe I shouldn't draw a dot. Let's see, I need to go, so maybe make this pi over 2, and then this is pi, and this is 0, right? So if I did graphing, we're going to graph this inverse because we can take each of these 3 points, flip the x and the y, and there's our nice graph, right? So instead I'll have 0 pi over 2, which is here in the middle, then -1 pi, which is here, and then 1, 0, which is here. And it's going to look, I mean, it looks like a straight line, like it could be, but it's not. Think of that cosine. It's going to look like something. Okay, like I was being dramatic on the curve maybe, but it's going to be something like this. Okay, so some type of curve, and that doesn't look good.
Yeah, right. Bad. I guess our internet connection dropped out. There she is.
Oh, wasn't that exciting, everyone?
Hey, welcome back.
Hey, I'm back. At least Zoom didn't drop. That's cool. Who knows what the heck just in there, but here we go. Let's okay. I mean, I honestly don't even know if I lost internet or what happened. That was very weird. But let's do this. We are here. Let me pull up the chat again. I gotta get my setup again. All right, bear with me, everybody. We're just having a time. Was there more in the chat? Was there a question? Because now I don't, I mean, I can pull up the chat tonight, but now I don't see the chat anymore. Did anyone have a question in there, or we're just, okay, I just lost everything. Oh, it was like, where the heck she go? What happened? Anyone else see her? Yeah, okay. You made McKenna the teacher. Perfect. All right, McKenna, don't be too stressed out about that, I hope. Okay, so, all right, well, so let's continue. Let's see if this happens again. You guys just get to deal with all the fun stuff, you know? Okay, so when we're finding inverse cosine of anything, we're only looking 0 to pi now. So we're only concerned about like this upper half, right? And so in this case, I want to know when is the cosine of an angle -1/2. So -1/2. So I know that x is negative over here, right? And so I have to think it's either going to be like 2 pi over 3 or 5 pi over 6. It's going to be one of the pi over 3, pi over 6 type of deal. or 30/60 type of deal, right? But just add 90 to that or add pi over 2. So I'm like pretty sure. So this one is -1/2 √3/2. And this is it 2 pi over 3? I think. I'm pretty sure it's this one. So the answer here would just be 2 pi over 3. Right. And again, maybe I'll write this for the next problem. I'm thinking that, or this is not a good thought bubble. I'm thinking, here's my thought bubble or whatever it is. Angle, or wait, this isn't, let me say this even better, just to be a little more concise. Cosine of what angle equals square root 3/2, right? This is the question I'm asking my brain, right? When I see something like cos or cosine -1. And so again, I'm going to look 0 to pi over 2. I know I want positive square root 3/2. So I know that the point, it should be positive square root 3/2 1/2. This is going to be the point I'm looking for. And I think it's pi over 6, the other one. So this should be pi over 6. Yay. And again, this does have everything to do with still memorizing that your like unit circle and these angles and these points, right? So if you still are like, I have no idea, like this is too much, have your literally like print it or write it or something, or Google it and just have it on your side of your screen or something, and be constantly looking at the unit circle. And I promise you, if you are doing that, if you are looking at it constantly and doing these problems, it eventually you're just going to be able to close your eyes and remember what is where, at least that would be, maybe that's the goal, at least till December, right? Then you get like a little break and then maybe you don't have to remember after that. Okay. So now we're going to look at tangent, and very similar so tangent, is a little bit, well, similar in that we're going to restrict the domain, but because it repeats itself. But tangent is a little bit different because it does this thing where it looks like this right here almost looks like x cubed, doesn't it? Like it kind of has that little snaky graph, but then it just like repeats a million times, right? Shouldn't okay, I just got something in the chat. Shouldn't 2a 150? Did I mess 2a up? Or I did it in radians. Are you meaning degrees? Yeah, so maybe I'm not totally sure, but I think I did radians. Maybe someone's doing degrees. But okay, if there's still a question, feel free to chat me on that. So for tangent of x, for the tangent, my restricted domain, we're just going to pick, we can do this entire function. We're just going to pick between our main two asymptotes. So it's kind of nice because actually the domain, it's the same -pi/2 to pi/2, but we're not including the pi's over 2, right? But it's the same as what sine was, except sine you include them, right? And then my range, I mean, it's still all real numbers or -infinity to infinity, right? And so now, fun twist here, we change our domain becomes is the old range, and the range comes from our domain. So now we swap these and we real numbers here, -pi/2 to pi/2 for the range. And so to do this, I would recommend, so if we label this could be like pi/4, pi/2, -pi/4, -pi/2. And then maybe we make these just 1, 2, 3, etc. -1, -2. Okay. So what's going to happen is our asymptotes, what we had before, they're going to move from, I mean, they're still at negative pi over 2 and pi over 2, but they're on y. They're going to be here, right? So let's draw those in. So now I have horizontal asymptotes instead of vertical, because remember I just swapped x and y. And then we can get this graph. And then somebody did ask to just look at 2a again. So we will look at that. Let's just finish this graph here. So in order to do this, I mean, my points, like this is 0, 0. So if I swap it, it should still be at 0, 0. And then you could pick like another point, like here, it would be pi over 4 comma 1. And like here, it would be negative pi over 4, 1, or negative 1. Okay, you can't really read that, but so now if I swap them, it should be, I'll write them on the side, 1 pi over 4 and -1 negative pi over 4, right? So if I plot these guys, 1 pi over 4 would just be here, -1 negative pi over 4 would be here. And then I know they go off, they don't go to infinity, they go off to the red dashed line to the asymptotes, to pi over 2 and negative pi over 2. And there's our graphs here. And these lines, this is y, negative pi over 2, and y equals 2. But over here, they were like these dotted lines are x equals pi over 2. And x equals -2. So they just trying to emphasize, I guess, more that they're switching, right? They're switching each other. And before we go on to examples of this, we just are going to go back to 2a. So I think someone's saying it should be maybe 5 pi over 6, which is the one here, which I think at the point, so if you look up your unit circle, and maybe I should have one up because I think I can picture it, but okay. It's, of course, like I'm clicking on one and it's not loading. That's great. Okay. Yeah, so we want, so I think maybe you were looking at part B, but we want, for this problem, we want -1/2 to be cosine. So we want this, and that's definitely the point at 2 pi over 3. We're not looking at the square root 3 over 2 in this problem, right? We want the -1/2, and that's going to be my cosine for 2 pi over 3. And if you're thinking of the reciprocal, like, so, oops, hold on, give me a moment. So over here, if I reflect this, this is like, okay, I'm probably not drawing this like accurately, but this is pi over 3, like 1 pi over 3. And this would be the point 1/2 root 3 over 2, both positive. And then we just wanted the 1/2 to be negative. But whereas this point here would be negative root 3 over 2, comma 1/2. And I wanted this -1/2. So hopefully that answered the question. Yeah, okay, cool, good. Okay, so now we're gonna check out, let's see what we know about arctan over here, okay? So for inverse tangent, what's weird to me, and I mean, maybe this is normal, but is like arctan 1 or inverse tangent of 0, it seems so weird. It sounds like, oh, we can't do that. Like it just sounds weird, but it actually is very nice. And so so remember, we're going again from negative pi over 2 to pi over 2 for these. But it's easy because you see 0, don't mix that up with angle 0. This is This is the point, right? So arctan of 1 means this right here means tangent theta equals 1. What is theta, right? So this is what we're looking for. Like, what is theta? And remember, if tangent equals 1, so I'm doing some scratch work here just to get to our answer. But if tangent theta equals 1, tangent is sine over cosine equals 1, which means if I multiply by cosine, I get sine equals cosine theta. So sine theta equals cosine theta. So if you didn't remember, like, what the heck is tangent? How do we get 1? You know, if you don't remember, you could just write something like this out. And as soon as I see that sine and cosine have to be the same, I'm like, oh, root 2 over 2 and root 2 over 2, it's pi over 4. Like, I'm just automatically, like, I can think of that, right? And if it was negative, it'd be negative pi over 4 because we're looking only in this range, right? So I want where these are the same, and that's going to be pi over 4 or 45, but I'm going to say pi over 4, right? And then for 0, so like sine, so sine and cosine of 45, Jakob says, yes, correct. So for 0, well, here's something interesting about tangent. Tangent, tangent passes through, hey, no, go back to sleep, okay? Tangent passes through the origin, which is at 0, 0. So, and we know this from our graph up above, they both pass here. Oh boy. I wonder what that translates to in the barking in the, if you're looking at, what is it called? The dictation or whatever. I wonder.
Oh, the closed caption?
Yeah, the closed captioning. I wonder if
it probably says bark.
Yeah, Scooby. Yeah, exactly. Yeah, that's what it's saying. But Kobe is my deeper barker. He's the loud. It's Kobe.
Oof.
Yeah,
Oof.
that's Kobe. Yeah, which they're gonna have to go outside in a minute, but he'll just eat his own poop. So then I deal with that too. God, they're just a lot. Okay, so tangent passes through the origin. So actually, I don't even have to. I mean, I could think about it, but I don't have to really think about it. Sine, inverse tangent of 0. It's where sine is 0. So okay, sine is 0 at, like, on the x-axis, right? That's 0. So this is just 0. So that's nice. I mean, you could overthink it, think about it more. Again, like you could say tangent theta equals 0. Sine over cosine has to be 0. So sine would have to be 0. Now, sine is also 0 at pi and 2 pi and all this. But remember, we're staying between negative pi over 2 and pi over 2, right? Excuse me. So yeah. So now fun stuff. And I really should pull up Desmos, but maybe if you guys, I mean, maybe I will on my other computer. Because, and if you have a calculator, just pull up the Desmos scientific calculator for this, or pull out your calculator. But for this, if we want to approximate in radians and degrees, so this means you have to change the mode. So again, I mean, I won't take too much time in class to be like, push this button on your calculator, but I mean, this is good for you to practice, and I'm sure it'll be all over the homework, so you can practice it there too. So like if I'm going into the Desmos calculator, I'm going to hit, what do I want? Inverse cosine. So arc cosine, and then I want 3. So you can do 3 divided by 5, and then, but make sure you have these parentheses and you don't take like arc cosine of 3 and then divide by 5, because that's going to be wrong. We want actually that'll give you an error, but we want the inverse cosine of 3 over 5. That you could even make it a decimal, 0.8 or something, right? 0.6. I don't know. Okay, I can't add. So if I want this in degrees, or maybe we can start with radians. Let's do this. So if I want this in radians, so I'm just gonna put this 3/5 equals, so I'll do radians first. And this is just a mode on your calculator. So if you really can't figure it out, maybe at the end of class, we can go through it. Oh, does it say to round it all? Yeah, it doesn't. So I'm going to write a bunch of these 9, 2, 7, 2, 9, 5. I'm going to write a bunch and then I'll kind of simplify. So we'll say this is like 9.3. Like I don't, 2 decimals is probably plenty. And then the inverse cosine of 3/5 in degrees is going to be, all you have to do is swap, enter this, but in a new mode. And I get like 53.13, or you could say 53.1 degrees. Okay. And these are whenever you have something in your arc or inverse trig function that you don't know, like it's not 1/2, 1, 0, √3/2, something like that. This is when you can just use a calculator, and they'll almost always tell you, like, use a calculator now because otherwise you'll never figure this out, right? Now sometimes, so this one says approximate the degree measure to one decimal place of the angle in degrees where this is true. Okay,
Can I ask
so
you a question there?
Yeah.
Can you draw a right triangle and
yes, so you could, so in
yeah,
right,
for 3/5 and
Yep. So
Like-
if we drew, right, and I said, okay, suppose like let this be theta or something, and theta's here, and I know arc cosine is 3/5, so that means this is 5, this is 3. I mean, this would be 4, right? But this means, I mean, it still doesn't tell you anything about the angle, but
Mhm.
what you just, but if you're curious, like about, okay, does my answer make sense, right? Like we got 53.1 degrees or 0.93 radians. So 53 degrees about, does that make sense? Yeah, that makes sense. If I got like 140 degrees, might not make as much sense, right? Or if I get 200 or something like really large, or, then I made a mistake or something.
It should be an acute angle.
It should be acute because it's inside your triangle, right? Yeah. So yeah, good. Now for the next one, so I'm going to write inverse sine. So theta is going to equal inverse sine of 3/8. So you could do the same thing, write that triangle, but again, for the angle, you'll still have to plug that in the calculator. They want degree mode. So let's change your calculators to, all right, I'm using calculator online, but it's like, yikes. 3/8. Okay. So inverse sine, but I wanted. Okay. Let's see. Yeah, don't know if that's working, but okay. So now here's the kind of weird thing about this one. They say, so when I do this, I get about 22.0, I'll say, degrees, right? Because it's like 0.0243, blah, blah, blah. So I get this, but they say approximate the degree measure, but they want it between this. And what that just means is, I mean, think about it. If we're here, sine is this, sine is y, this up here. So like if I have a point anywhere over here, that's, this value is the sine. So what they want is, they're just saying, instead of typically the angle you get for sine will be between -π/2 and π/2, or like 0 to π/2. Oh boy, I'm freezing up. This is not good. Okay. Oh, maybe I need to charge my laptop. All right, folks, let me just plug in and kind of relocate a bit. You're not going to be able to see me because of this window, and I just didn't plan this well, but okay, maybe my laptop, maybe my personal laptop is just dying on me, and it's just deciding.
Like a confidential informant or something.
Yeah, it's like stop doing what you're doing, right? I mean, I have a really nice work computer, but I can't teach from that. So, okay, that's more confidential than my personal, just 1,000 pictures of my dogs, right? Okay, so I get an 22. which is, like somewhere there. I want something though between 90 and 180. So I want something in this section here, the blue. I want something there. Now to do that, well, if this is the point, right? If I made a right triangle, I could just reflect it over here, and this angle, well, that angle will be the same as this one, right? So these will be the same. And so what I can do to figure out what would this whole thing be, like what would this be, I would just subtract, I would do 180 minus 22, because I'm just taking away from 180 is like this whole thing, right? Oh, look, now we got a rainbow here. So 180 is this whole thing. This is 22, and get red, the red I just subtract, right? So I'm going to do that. And what do I get? What should I get? 158. So about 158. So theta is about 158 degrees. And it said, okay, to one decimal place. So maybe I should write a point so they know, like, we didn't round this. This was like officially points. Okay. So there's some calculated there. Okay, great. Now we're going to apply inverse trig to some type of problem, and this one's about the Eiffel Tower. How interesting! I've never been. Wish I had, but maybe one day. So the Eiffel Tower, they're telling us, is 1,063 feet tall. Maybe that's true. Maybe it's not. I'll have to click to fact check, right? We should have a fact checker for all these word problems. A measurement is taken of the length of the shadow of the tower. Okay, this is a lot. So, okay, height of the tower. We know from here to here, they tell us, is like here. They tell us it's 1,063 feet. They want us, the shadow, so they're saying a measurement's taking of the length of the shadow of the tower. So suppose the shadow, I don't know, this way, right? Because I already drew the other way, maybe. But the shadow of the tower will be in some direction. And it's found to be 310 feet in length. So the actual shadow, which the shadow is on the ground here, they're saying this is 310 feet. That's what they're measuring. Wow, this may be horribly not drawn to scale, but this is fine, right? So they're saying approximate the angle of elevation of the sun. So angle of elevation is at the bottom. This would be this angle. If they said angle of depression, it's the one up here, but elevation, right? So you're looking up. To the sun, we also pretend that, the sun is up here, maybe, to the nearest 1/10 of a degree. Okay, so let's figure this out. So I know my height, I know my 310, my adjacent side. So I have adjacent and this is opposite. So I'm going to use tangent, right? So tangent of theta, because I could find this side, but then I have a square root, then I'm being a little extra. I don't want to do that. So tangent of theta is going to be opposite. So 1,063 over so 310. And so to get my theta, it's going to be the inverse tangent, or arctan, whichever you prefer, of 1,063 over 310. Excuse me. And then I hand in the calculator and that inverse tan button, and I have in parentheses 1,063 divided by 310. And okay, I'm getting about 73. Make sure you're in degree mode. You'll know because you'll get some weird decimal. Yeah, awesome. Jakob got the same thing as me. I got about 73.7 degrees. And just something to note, like remember, I think from the textbook, they remind you, the answer to an inverse trig function, you're like, where am I going with this? Is an angle. So my reminder here is just like, reminder is you got to put degrees. If you don't put anything, I'm going to assume you mean radians. So just put that little degree, right? Because, and you could write radians if it was in radians, but typically radians has no label and degree has the little teeny tiny circle. Okay, awesome. Now we've got some crazy practice problems to do here. So we're getting wild on our Tuesday night class, right? Okay. So, and what I mean by that is just that we're looking at sine with arc sine or sine of sine and all, we're combining all the wonderful knowledge our brain has, and we're going to challenge it a little bit. Is everyone, oh, sorry, everyone good with this problem? Yeah, okay. I'll take no chat. You know, McKenna's just happy that she's not the teacher anymore, right? I'm just kidding. Okay. Okay, so now here's something where we're going to use the inverse trig function, but, you know, I mean, it will almost always think it is, but times it's a little bit complicated, right? So looking at this here, if I see arc sine and sine, I know that arc sine is the inverse of sine. They cancel each other out. Like think about when you do this, oh my gosh, okay. When you do, okay, if you have f of x equals x squared, right? And okay, but let's say you're only doing 0 to infinity because then it's not a fun, like, so just part of it. Then f inverse of x is square root of x. So if I had like 5 squared, and then I take this, and then I take the square root, I mean, what do I get back? Just 5, right? Like 5 squared, square root of 25 is 5. So 5, okay. But if I did negative 5 squared, notice, and I take the square root, this also equals 5. So this is not in, hold on, let me not write this. So this equals f inverse of 5. But f inverse of negative 5 does not exist. D, hopefully, if you need me to write that out, I'm sorry, I ran out for like this. But so sometimes, like I said, sometimes it'll be just like this. And you're gonna say, oh, square root of 5 squared is 5. We have problems, we don't have to think about it. But sometimes you'd have square root of negative 5 squared, and oh, and it doesn't equal square root of 5. What did that? It equals 5, right? Oh my goodness. And you think, oh, something like that's not looking right. Like an inverse should reverse whatever's happening, and it should be the same thing. So basically, my whole spiel here is to tell you that, well, this answer should be negative pi over 6 because I take sine of negative pi over 6, then I take arc sine. And the good news for you is that this one is true. We're going to check to see why. But this is true. So sine of negative pi over 6, if you think about where the heck is that, negative pi over 6 is this guy here, right? Or somewhere around there. So 0, negative pi over 2, this is negative pi over 6 over 2, right? So this is this guy. And the point there is what, root 3 over 2 negative 1/2, right? So that my sine is I have negative 1/2 here. So then I'm doing arc sine of this. Now the reason this works, right? So why does this equal negative pi over 6? Cool. The reason it works is because oh my goodness, negative pi over 6 is already between negative pi over 2 and pi over 2. So already in our domain, right? Like our domain for sine, remember, is this here. So it's already in that domain. But if we look at this next one, right? 7 pi over 6. Okay, where's that at? Here's 0, pi over 2, pi. 7 pi over 6, that's over here. And remember, it's very similar to the point here, but this is 7 pi over 6. And I'll say this was negative pi over 6. And very, but this is negative root 3 over 2, negative 1/2. And so sine of 7 over 6 is still negative 1/2. And then I'm still taking arc sine of it. But my answer, because I am in that domain, is just negative pi over 6. And sorry, there's a question in chat. How did you get negative pi over 6 in? Kevin is, yeah. So, okay, in this case, you're not using your calculator. Your calculator 100% will give you decimals because your calculator doesn't know. We're getting pi over 6 from the unit circle. So I'm basing everything off of like in the unit circle, these, and then like reflecting them based on the quadrant that it's in. So Joseph, hopefully that answered the question. Yeah, okay, cool.
Could you explain
so
to me
yeah.
again, though, you started off with the sine of 7 pi 6, which is on in the third quadrant, right?
Yes. So
Okay.
I got, so sine of 7 pi over 6 is third quadrant, but it's -1. It's in the third quadrant and it's negative 1/2. So I solved for it, but then you'll notice this here and this here, they're the exact same thing, right? Although these angles were different to start, their answers when I evaluated sine were the same because sine repeats itself, right? But when we're doing arc sine, we limit that repetition and we only allow it to be between negative pi over 2 and pi over 2. So we only allow the arc sine answers to be in that domain because, and the reason being, kind of like this, kind of like the x squared thing. I was saying x squared, if I just do this piece of x squared from 0 to infinity, this is a function. This has an inverse. But as soon as I add this, it like ruins the inverse because I get things like this where I can plug in. So if I was to get inverse of that, it would have to be restricted on the domain where from 0 to infinity. And so I would have to say it doesn't include this, just like we were blocking off of sine and above, I would have to block this off.
So the inverse
say,
has to be in the restricted zone.
Yes, exactly. Inverse is only in that restricted area, but the sine, we could take sine of any good old angle, and so that's what makes these problems, they can be tricky, because if you remember, oh, this is between, I'm erasing. If you remember, oh, like this is between negative pi over 2 and pi over 2, I don't have to do any work. It's just going to be the same thing. Then that's great. But then we get to cosine, and cosine, remember, was between 0 and pi. And so 7 pi over 6 is just here. Okay, like this is again not drawn to scale, but this is 7 pi over 6. And so cosine of that, well, I just drew that point. That was, this point is the same point that goes here, right? So I just drew that. So if I want to get my cosine of this, it's negative root 3 over 2. So then I have inverse cosine of negative root 3 over 2. And I don't care what the y is. I'm looking between 0 and pi. So what I'm looking at is I'm looking at this point, like this is negative 2, but up here. So now instead of 7 pi over 6, maybe I should do a different color for all this. I reflect it and I'm just going to get 5 pi over 6. Oh, somebody said you can write the equation, Jakob, you can write the equation in the calculator, arc sine of sine of pi over 6, and it gives you 5 pi over 6. Is that, if that's true, that's, you got a good calculator. That's cool.
Yeah, it is giving me the answer.
Okay, cool. Some calculators though, and there's probably a setting that you just have to do, because I think someone else was saying, oh, Joseph was saying he keeps getting decimals. So there, Joseph, for either your calculator is just going to do decimals, or there's a setting where you could probably make it be fractions, or you could change it to degrees and it will give you like an exact degree, right? And then if you want to okay, see, yeah, okay, so cool. So, okay, so in this case, so now we have our angle, but notice how these do not match. Even though we're taking the inverse of a regular function, they just don't match because it's not in the domain, right? But we'll notice that here, point and point, these have the same cosine, and we want our answer between 0 and pi, right? So that's why we change from the black I put to the blue dot, right? Okay, now let's see if this one's any different here. Okay, so cosine of -1/2. Oh, so this one is, and at first I thought it should be arc cosine, but no, what's happening here, so if you're, I mean, this is going to be just basically probably a calculator problem or something, but what's happening here is that this is an angle that's in radians. Even though there's no pi, it's a decimal and we're taking cosine. So remember, there's no degree. Like look at, if you, well, okay, these were all in radians because they have pi's. So this is an angle in radians. And so we're taking, so I don't really know like what this is because this is going to be a decimal, but let's take a look. But if, so pi over 2 is like 1.97 something, I don't know. But so 0.5 is going to be somewhere between 0 and pi over 2. So like maybe it's here, you know, maybe this is 1/2. Oh, but I want -1/2. So it's going to be over here. So I want -1/2, right? This is -1/2 radians. And that's our theta. And so what I want though is this one here. So this would be 1/2 radians because I want something between 0 and pi. And so you could put this in your calculator. It'll probably give you the right answer. But yeah, so Jakob's getting 1/2. But you could also just draw this picture and realize, okay, I have -1/2 radians. I want just +1/2 because it has to be between 0 and pi. So this is just, so whatever this equals, you know, call it like, I don't know, call it like P. When I do inverse cosine of P, I just am going to get the pi. I'm going to get the same angle, the 1/2, but it's going to be the positive one reflected. So we don't even care. We don't care what this is. We don't need to know what P is. We can just say, okay, will be +1/2. Or you could put it in your calculator and be happy. Now these ones say find the exact value. So what this means is you could check it in your calculator, but you want to get the exact value. And this is where, granted, actually some calculators will give you the exact value. So again, here you, how lucky are you guys, right? But here we're looking at arc sine is inside the trig function, which we haven't seen that yet. So this is going to equal some theta, arc sine of 40 over 41. This means that sine theta equals 40 over 41. And so remember, this is like opposite over hypotenuse. So if I'm gonna draw my right triangle in somewhere in here, right? I'm gonna say, and I'll just guess that it's up this way somewhere, right? So suppose this is theta. My opposite side is 40. My hypotenuse is 41. I can just solve for that third side and figure out in part A and figure out what's going on here, right? So this is for part A. So if I just find this side, then this is cosine theta, and it's just going to be adjacent over hypotenuse, right? So I don't have to do any fancy work here. I mean, I have to do Pythagorean theorem, right? So I'll do 40 squared plus b squared equals 41 squared. And then b squared is, so 41 squared minus, it's like 1681 minus, I think 600 maybe. Oh, and that's 81, so that's nice. And so b is just 9. So this is 9. So my answer is just 9 over 41. That wasn't so bad. Now, where this gets just slightly tricky is when I'm given a negative number in here. Okay, so this here and this negative, we want to pay close attention because it has to go. Remember, the hypotenuse is never negative in our right triangles if we're drawing them on the unit circle. So hypotenuse is never negative. So that means the 40, the opposite side, is negative. So what this means, let's do a different color. What this means is that, oh wait, so I'll do kind of what I did here. This is theta. So sine theta equals negative 40 over 41. And so that just means that this is positive 40. This is positive, oh no, this was 9. This is positive 9. So if I want to get negative 40, okay, I should it's maybe about here, right? Negative 40, okay, this is again, not drawn to scale, but it would be somewhere like that where this is still 40, but it's just going down, and my angle, my right triangle is here, and okay, my little angle, my theta is in there, my hypotenuse is still 41, my side is still 9, this side is still 9, because it's the same triangle, it's the same numbers, like the same triangle, but it's just flipped across the x-axis. So now, if I want cosine of that, it actually is going to be the same thing because cosine doesn't involve the opposite side, right? So this is actually going to equal 9 over 41. But the picture just looks a little different because my signs are different here. Excuse me. Okay. So we have, oh yeah, question? Oh, you want me to pause? Sorry. Yes. Okay. Yeah, hopefully I'm not going too quickly, but so one of our sign, oh yeah, so let's emphasize what Joseph just said, just because as an aside. So aside, I want to change this the other way, but 1 over sine x is not equal to sine negative 1x, which I know that's like not intuitive, or maybe I should, but if you're thinking, what the heck is 1 over sine x? Well, 1 x is cosecant x. That's what we call it if we don't want a fraction. We do not call it the inverse of sine. It is the reciprocal of sine, right? It is, and that's why trig functions, they are not like numbers, right? Because okay, I'm going to erase this because it is confusing, but like 1 over 2 is 2 to the negative 1, right? For numbers. So numbers are one whole ball game. Trig functions, whole nother section, right? Different compartments, just like you got marketing, sales, whatever, accounting, like they're different departments here. Okay. And so although they have some things that are related, they are not the same. They do not have all of the same properties. Just like trait functions have some fancy properties or, things about them where regular numbers don't. And this equals the inverse of sine x. I don't know. So that is something very important to remember, and that holds true for cotangent, et cetera, et cetera. Yeah, so that was a good.
Kind of funny how part D has part A and B it's like letters and then letters again. I don't know. Just thought that was
yeah. Well, so
it's like six, like number 6, part D, part A of part D.
Oh, are these all? Yeah, these might. Oh, yeah, it goes from 6 to. This. Okay. Yeah, so this was a typo, and actually I fixed it in the later version, or you guys don't have the fixed version probably, right?
No, that's what mine looks like.
Yeah, so right, but I'm saying I fixed it later, but I think I posted it before I fixed it. So this here technically is 7, and then this would be like 8, 9, right? Like technically. Okay.
Okay, because we do have it does go to number 7 next, but anyway.
Well, yeah, it does.
Well, you made that like 8 and 9.
But do you see what I'm saying? Like, so, I mean, okay, yeah. I did change because this is not supposed to be DAB. It's supposed to be 7. So when you're typing this, you just have to hit enter again. And basically, that's what's happening there.
It does it for you automatically.
Yeah. So when I was typing this, I did not hit enter again. This is what happened. So yeah, I was like, what do you mean DA? Yeah. Yep.
Yeah.
But okay. So good thing to bring up, Joseph and German. Yes. I guess I could actually turn this light. Okay. So number 8 or 7, whichever your heart desires. We're gonna say, so we have cosine of inverse sine of x. So this would be like our theta. And we want to write it for x is 0 to 1 as an algebraic expression. So it's a little bit weird here, but bear with me, right? So this is saying sine of equals x over 1. So think of this as the opposite. Think of this as the hypotenuse, right? So now I'm doing basically what I just did. Oh, and actually, I don't need to draw the full. I just need to draw a right triangle. And I have my theta. My opposite side is x. My hypotenuse is 1. So if I want to solve for this miscellaneous, we'll call it a side, I'd get a squared plus x equals 1 squared. So a squared is 1 minus x squared. And a is the square root of 1 minus x squared. Now, this isn't going to look necessarily pretty, but that's what it is. I don't know what x is, so we leave like this, right? So now I can say I was looking for cosine of this, right? So cosine of theta, which we called theta inverse sine of x, is going to equal my adjacent, so my a side, over my hypotenuse, 1. So square root of 1 minus x squared divided by 1, which is just square root of 1 minus x squared. Right? So there's my cosine. And that's writing it as an algebraic expression. And notice how x is between. The reason for this is because if x was 2 or 5, I would get a negative number inside that square root, and that's imaginary. And we're packing up imaginary numbers that are not existing in our world right now, right? So that's why that domain, although you may not notice, like, yeah, it's fine, but that's why they say it in the problem, because it's true. It's an accurate part of the problem. Okay, let's keep going. So now I have arc sine of 2 over x. And it just write sine, call this theta. This is, so this whole thing is theta. And this is telling me that sine of theta is 2 over x. And so again, I can just draw a right triangle. Doesn't matter. It could be this way. Like, it doesn't matter, you know, as long as opposite side is 2, my hypotenuse is x. And then this question mark side is going to be 2 squared plus, okay, now I'm calling it b squared equals x squared. And so I get b squared is x squared minus 4. And then I take the square root. So this side is square root of x squared minus 4. And then I want tangent of that angle. So tangent, and I can just do TOA, right? So over adjacent, so 2 over square root of x squared minus 4. Now, here's where typically we'd make you like rationalize this or something, but that's just not fun. So I'm like 9, well, I know that in the notes we leave it like this and in the book, but I'm pretty sure your homework, you could probably leave it like this as well. Because otherwise it just gets kind of a little to be a little too much. Okay.
In the book, it said something like that's used a lot in calculus. Is that right?
Oh, okay. And maybe that's why they leave it like that. Yeah. So yeah. So this is, oh, actually I'm blind and just need to read. Do not rationalize the denominator. Look at those lovely directions. Yeah. So we got to pay attention to that, or I need to pay better attention. Okay. So now number 9 or number 10, whichever you want to see it as. Now we're looking at secants and cosecants. So when we do, basically going on here is when we do inverse of these, we just convert to sine, convert to cosine, do what we normally do, right? We're not going to stress with inverses about memorizing anything about cosecant, secant, cotangent. We're just going to convert it to sine, cosine, tangent. Boom, there you have it. Because then it also gets really confusing with the whole over bit, the reciprocal. And yeah, and someone's already stressed. Yeah, Jakob, sorry. But so we're not going to stress, and we're just going to convert it right away to sine or cosine and then deal with it like that, right? So I'm not even going to think about what the heck this is saying. I'm just going to say which one is secant. So secant is cosine. So this is inverse, or oh, oops. Well, okay, I can't literally just rewrite it. So we do a little bit of work, right? So first what I'm going to say, let's let this equal, know it equals an angle. We don't know what that angle be. We're going to figure it out. Oh my God. And look, this it should be B, not C, right? I definitely took stuff out of this, and that's why, and rearranged, and then totally messed up and didn't give you the right thing. Okay. So for part A, I know this equals an angle. So if I want to rewrite this as secant theta equals 2, that's what's happening, right? This is what's happening. And then I would say, okay, secant is 1 over cosine equals 2, right? Sorry, I had to think about that for way too long. And so now I could this, or I could say this is 2 over 1, flip it and say cosine theta equals 1/2. And now I'm really comfortable. Now I know 0, pi over 2, pi. I know exactly where cosine theta equals 1/2. And it's at this guy here, 1/2 root 3 over 2. And that's pi over 3, I believe. Right. So I'm looking for this. I'm looking for this. And I know this happens at pi over 3. And so my answer is pi over 3. And I don't even, all I have to know is that secant is the reciprocal of cosine. Like I have to know which function it goes with. And then for this next piece, let's let this equal theta. So I would get cosecant theta is -2√3/3. Okay, this seems complicated, but it's not going to be, promise. Oh, sine is different y restriction than cosine, right? Oh, yes, yes. So sine is like -π/2 to π/2.
Sorry, not sine, it's secant.
Oh, no. So secant and cosine will be the same restrictions, and sine and cosecant will be the same restrictions, if that makes sense. Like, we didn't have to worry about the restrictions of secant because we just focus on cosine. And here we're not going to have to worry about the restrictions of cosecant because we'll just focus on sine. So the nice thing about this is if you think like, okay, if you think the reciprocal, so I'll write this up, reciprocal, this is the reciprocal of sine, right? And so if I want sine theta, I'm just kind of skipping this step here where I write 1/sine. If I want just sine theta, I take the reciprocal of this, right? And I say, okay, -3/2√3. And I'm going to have to rationalize again because it's back in the box. So, okay, let me rationalize this and say, so this is going to equal -3√3/2 times 3. I could say 6, but I'm gonna, because I'm just going to erase. Oh, I'm going to cross these out. And then I get -√3/2. And remember, we're going -π/2 to π/2 because we're looking at sine. And I want -√3/2. So I know that that's going to be over here in this quadrant because I want -√3/2 to be the y. And so this is going to be, I think, -π/3. Yeah, because this is like π/3. So this will be -π/3. For A, just out of curiosity, secant -1 isn't the same as 1/cosine -1. Yeah. So I want to say no, but I can't remember why we don't, like, I don't remember the reasoning we don't do that because it might be. If you put it in a calculator and they're the same, then it is. But for whatever reason, the book has us convert to an equation with just regular trig functions, then transfer it to sine or cosine, and then solve, right? So I would play, if you're super curious, I would play with it in your calculator. And if you're getting the exact same decimals, then they're the same. Yeah. So again, you're right, in your calculator. So I think it should be, well, so you could do this in your calculator. What you could do is 1/inverse cosine of 2. Oh, I don't think that worked. You know what? It's not the same, but what it is it's the inverse cosine of the reciprocal of this number. So if you wanted to do this in your calculator, it's inverse cosine of, and you would take this number that's inside secant and just do the reciprocal, so 1/2. Or this guy here, you would do inverse sine of -3/2√3 if you did this in a calculator. Okay, yeah, so you would flip it. So instead of flipping the trig function this time, we're flipping the answer because usually we don't know the answer. Yeah, exactly. It seems more complicated, hence what we just did is maybe slightly easier than that. Yeah. So for this next one, okay, so maybe this is really relevant, Joseph. So good question. Inverse cosecant of 8/5 in radians rounded to 4 decimals. Oh boy. So what we want to do is we want to say inverse cosecant of 8/5 is going to equal some theta. So what this means is cosecant of theta is 8/5. And therefore sine of theta is 5/8. Now, in your calculator, you can do inverse sine of 5/8. And this will get, remember in radians, and it said 4 decimal places, so it was like excuse me, 0.6751 is what I got about. Yeah. And this is radians. So you don't have to write anything because it's radians. If you really love to write something, write radians. Yeah, and this is the perfect example. So Joseph, your question, it was almost like you knew what was coming, right? Somehow. Okay, and we added, so I forgot we added this. I thought we were stopping here today, but so I'll go through this, but we added this kind of last, it wasn't taught in the previous semester. So, yeah. Okay. So inverse of cotangent, I mean, again, similar thing. Maybe I won't write as much here because, so inverse of cotangent, here's the cotangent function is like tangent. It just repeats, right? But we're just going to focus on 0, or so maybe we're going to focus on 0 to pi. So what's important here is just the domains. So restricted domain is going to be, and we're not including, oh my goodness, I already messed up. It's 0 to pi, not including. And then the range is still -infinity to infinity or numbers, right? And so again, we just reverse these over here. So my domain is all real numbers. My range is 0 to pi. And you'll see like the point in the middle is that in this case, it's pi/2, 0. So in this case, it's 0 pi/2. And then they kind of just, I mean, you could pick another point just like we did with tangent and you plot that and graph it. So if we want the inverse cotangent here, okay? So if we want this, again, the best way, I know this is weird, but the best way to set this up is set this equal to your angle and rewrite it as cotangent of theta equals -√3/1, right? And so, okay, there's like 4 different ways you can go from here, but one way is if you figured this out or could figure it out, this is the same thing as -√3/2 over 1/2. If I divide each of these by 2, and remember, cotangent is cosine theta over sine theta. That's what's happening here, right? Cosine theta over sine theta. Now, if you couldn't figure that out, you change it to tangent, then change it to like sine cosine. You could convert this even more and switch it back to something you know, like tangent, sine, or cosine. Or you could draw your right triangle as well and try to figure it out that way. But whenever I see square root of 3, I know divided by 2, it's got to be square root of 3 over 2 and 1/2, right? Those are my 2 points. So really what we just need to figure out is where is this angle from 0 to pi? Because, right, our domain, remember, our restricted domain for cotangent is going to be 0 to pi. So I want to figure out where is the cosine -3/2 and the sine +1/2. Well, it's definitely going to be over here, right? Because it's not going to be over here. It'd be positive. So it's not going to be there. And then I just have to figure out where is it -√3/2, 1/2. Like, where is this point? Is it the pi/6 or the pi/3 type of deal? Is it 2 pi/3 or 5 pi/6? So again, this is staring at your unit circle. This is going to be 5 pi/6. And so I can say, let's see, I'll just say cotangent inverse -√3 equals 5 pi. 6. And I just rewrote the problem here, right? Now, there are different ways you can do that. You can convert it in other ways and things like this, but okay. So we'll do this calculator one, and then the extra practice, maybe I can, we'll skip this for now. If we do have time in another class, we could always come back and finish, or this is kind of extra practice for you to work on. Feel free to email me about it, come to office hours about it, so stuff like that. And technically what we were at 11, like technically this was 12 and this was 13 and this is 14, but doesn't really matter. So using a calculator to do this, we want to do exactly what we did before. Cotangent inverse -2 equals theta. So I get cotangent of theta equals -2. And you could think like over 1, right? So then tangent of theta is -1/2. And then this does exist in your calculator, right? Inverse tangent of -1/2. And let's just enter this real quick. Inverse tangent -1 over 2, because I don't that. And we want radians, I think, right? Yeah, radians rounded to 4 decimals. So this, I got about -0.4636. Make sure, did you have a -1/2 and inverse tangent and not 1 divided by that? Oh, yeah. Okay, so you want inverse tangent. And I'm gonna, I want to stop here so that I can put up the answers from the quiz in these last 5 minutes. And I'm sorry, I really thought, I think some nights we will end with a bit of time at the end, but we're not ending so early tonight. So I just want to make sure I get those quiz answers up for you guys, and maybe just talk through it. And yeah, -0.4636, that is correct. Good. So hopefully, I mean, feel free to try this problem. It is extra practice. I mean, it's unnecessary. So I'll put out of time, and maybe sometime we can come back to it if people are curious, but it's just another extra practice. It might be similar to a homework question. I'm not entirely sure. But okay, so let me save this before like all of my internet drops again and we make someone else the teacher for the night. Notes on my iPad, sure, save. Okay. Now I want to find the quiz. Where did I put it? Oh, quiz 3 key. This is great. This was your quiz, right? Yeah. Okay. Whew, got it. So for the quiz, this first one, I did take a point off. Some people rewrote it, which is fine because like they know, oh, sine and cosine is 1, but it was asking to factor. And so what it wanted you to do, and a lot of people, you know, wrote this out, is like a squared plus 2ab plus b squared is just a plus b, like times a plus b, right? So I was looking for just sine plus cosine, right? Okay, then verify the identities. Okay, there were like maybe 3 different ways that I saw people do it. And some of them, I mean, were really good. Some of them were the way I did it. If you tried it and got somewhere, I did give credit. If you like couldn't get to the end, I tried to be fair and not take 2, like these were each kind of at a 2 points-ish. And I tried to take maybe a half point or 1 point. But if it was totally not there, it was 2 points off. So for this one here, you just use even and odd, and then you just change secant in terms of sine and cosine, and then you get the right-hand side. For this next one, part B, you rewrite cotangent in terms of sine and cosine, simplify, and then you just get the right-hand side, right? Like I said, there are different ways you could have done it. This is just the way I did it. And the way I did it was I changed cosecant squared to 1 over sine, and then I had cosine. I got cotangent, and then I used this guy here, well, -1. I made it, I used that and said, oh, this is equal to cosecant -1. Now, some people showed a lot, now I think the point probably these are like book problems. The point probably is that you show more steps to show why this identity is true. I was lazy, didn't, but if you did, that is awesome. If you didn't, you were like me and you still got it right. So good job, right? And then part D. So this was tricky, but I tried to outline this for you guys in the yellow. I took this and I rewrote, these are the other two, if I divide by sine and cosine. And I basically plugged them in to this and this here, right? So I just plugged them in and then distributed the negative, these canceled. And a few people did it other ways, which was great. And a few people did it this way and they said, is this correct? They wrote me a note like, is this right? This seems like simple. And it is, it's just a verification. So it's just showing, oh, based on the identities I know, this is what we can do. And then number 3, most people got it. Maybe they mixed up a sign or something, but square root of 6 minus square root of 2/4 and negative root 2/2. Now this answer, if you got something funky like square root 2 minus square root 3/2, some like other thing, it was, and I marked it correct. That's because it is correct. You just did it slightly differently than how I did it, and that's all. But the answer, if you got that decimal, it's the same thing. So yeah, so hopefully that helps. So that is the quiz. Let me get to the question we're going to do today. Okay, now I'm going to do some of these questions. They are meant, there's no wrong answer. Well, today I'll do a fun one because I feel like class maybe was stressful, but next time I have a question that might be stressful. I will post the quiz and the notes from tonight. Just give me like an hour after class because I'll take my dogs out and then I'll do that. Okay. But yeah, Veronica, I will post that in the solutions on Blackboard somewhere. And maybe I'll finish this so that I don't like lose it. Look at it. So the question for tonight, and can you move homework? Yeah. So the homework, well, you're asking Michelle for 6-1, 6-2, or 6-3, or all of it. The written. 6-1 is due today. 6-2 and 3, I think, is due Thursday, but I can 6-1. I think you can submit it late. If not, I'll adjust. And I'll just grade it when it, but yeah, I can update that. Yeah. Thanks. Okay. But question for today is just going to be, are you a camping kind of vacation person or a hotel kind of vacation? Or maybe Airbnb now that we're in like 2022. And when I was vacationing, that was like not a thing. So go ahead and tell me, oh, I see some glampings. Yeah. So this was an easy question for today. Just for me, not as fun, but some people are total campers and some people are hotel people, some people are stay at home. They're like, this COVID thing was the best thing that's ever happened in the world because I don't have to go anywhere, yeah. Right. Yeah. And whichever you are, this is fine. I'm not judging. But so that, let me stop sharing this. And class is done. So if you guys, just make sure you answer the question in the chat. I'm going to stop.
Recording stopped.
Yeah. And you can like both. Yeah. Austin, definitely, unless you're camping in like January, right? But that, and one way that you could have solved that, I think that might help, is if you made a right triangle. So if you did tangent theta is -4,1, and you made a right triangle, and you wouldn't know, I guess, where theta was, but I think if you did that and the opposite side is 4, the adjacent side is 1, you could figure out the hypotenuse side and then even try to figure out like inverse side would be or inverse instead of tangent, if you didn't know. That might be one way. But again, we can, if there's time today, we can look at it. And if not, send me an email and I can either go through it the next class, just remind me, or I can go through it next class, or I can, like, in office hours next week, or just send it to you, something to you via email if we don't have time today. Okay. Okay. Give me a moment to get my setup here. Okay. All right. So hi, everyone.
Recording in progress.
Let's get started. Today we're going to do section 6.5. Oh, and I didn't save what I wrote at the top. I spoke to somebody and I remember. So I wanted to just start class by asking if anyone knows how this works in ALEKS. So if you want to review old homework questions, I know we've discussed this before, but I just don't remember. What do you need to do in ALEKS? Like, I think you can view it again, correct? Or do you have to?
You click on your grade, you go to the assignments list, and in the column that's sort of on the right side, it shows your percentage complete or whatever. You click on that and you can look at the report, and that is the problems and your answers.
Okay. Thank you for that. I couldn't give an answer for that. And I knew we discussed this before. So in order to review in ALEKS, you would go to your grade, look up the report, and then you can review questions and your answers. So this is a good way if you want to study the homework problems. And I just wanted to talk about that at the beginning of class. Now, also note that I posted today it's confusing because I think I called them both the same thing, but there's a test review and a test practice, which I should call practice. I should have called it just a practice test, but I think I called it also another review. So next week, we are going to do the 4.2, 4.3 notes. This is like just a review topic of logs. It is not on the test. And then we are going to do this test practice on Tuesday. But the review, I will post the solutions tomorrow. Because the review is the one where it has like 30 or 40 problems, and they're all from the textbook, and it's a bit overwhelming. The practice is very similar to your test, and your test has, 10 to 15 questions. I don't know exactly, but like some of them have A and B, right? So it's something like that. Keep in mind that the test review, all of 35 questions, you do not need to stress about doing all of this. But I posted it today, so you have a whole week. And then I'm going to post the answers tomorrow, so you have the answers as well. And on Tuesday, I can take questions next week. After we go over the practice, I can take questions on the review. So I wanted to just announce that at the beginning of class today. And also 1 week from now, I guess we have the test, right? Yes. And Joe, that is the 13th, correct? Yeah. Thank you. Okay. Oh yeah, sorry, David, I didn't see your chat. I'm a little out of it today, but we press on, right? Okay, so today doing section 6.5. This will be the last section for this test, right? And remember, this test only involves information starting from 5.5. So we kind of skipped like 5.5, 6, then we did like 6, 1, 2, 3. And then 5.7 and 6.5, right? But it's only going to cover these sections. So they were looking again at solving trig functions, and a little bit more about knowing kind of the unit circle and just how to solve like trig equation functions in them. So this first one, this makes us feel good. If you see this, hopefully you feel good, because I do. So if I see sine of x is √3/2, I know I have options. If I'm going to give a solution from 0 to 2 pi, if this is what I'm going to do, right? So this is 0, pi/2, pi, 3 pi/2, right? And then, well, 2 pi. So I know the sine is positive √3/2 at these, okay, like, well, at this place. So point, which means it's at this angle, then also this angle. But if I go down here, right, it would be negative. So I don't want those answers. So I'm going to get between 0 and 2 pi, I'm going to get two solutions. And hopefully you kind of remember, but I'll write what these points are. Like this is 1/2 √3/2. This is -1/2 √3/2. And the angles are pi/3. And I'll write it in this color. Pi/3, small one, right? And then the big one is 2 pi/3. So, and I guess you could write this, it doesn't ask degrees or radians. So if you want to write it in degrees, you go for it. But our solution from 0 to 2 pi is a set. So, oh, that was a pretty bad, oh my God, I can't, okay. Like something, it's a set that we'll write in brackets. So it's pi/3 and 2 pi/3. Okay, so this is our solution set for sine of x is √3/2. Now, if I graphed sine x, right? So here's the graph. Here's sine x, overall, like right here, right? This is y equals sine x. If I look at this graph and I look for this is the line y equals √3/2. And that's what we want here. Sine of x is √3/2. So if I look there, I see there's like 2 points here, 2 points here, 2 points here. If I kept going, there's infinitely many solutions to this, right? Because I could draw sine I could keep adding 2 pi or subtracting 2 pi and keep going and get more answers, right? So I see these were the answers I gave, pi/3, 2 pi/3, but then I could have done these over here, which would have been, going the opposite way, negative through 4 pi/3, and then negative like 5 pi/3 or something. That's what these are, I think. And then I also could have kept going past 2 pi and gotten more answers. So what do we do about this? Well, this was our solution on 0 to 2 pi, but our general solution means like all, like, because what we see here from all of these and these and those, right? We see that there are infinitely many solutions to this equation. We're still looking at this equation, right? In general. So our general solution is going to be these brackets again, and we'll say x such that x equals pi/3, over 2, of course I wrote that, pi/3, because pi/3 is our first one. We'll start the first one. But it's pi/3, but then I could add or subtract 2 pi to this. So I'll say plus 2 pi n, okay? Then I'll say, or x equals 2 pi/3 plus 2 pi n, and we'll say n is an integer. Oh, maybe that was also okay, better. So basically what this is saying is, if I take, my pi/3 point, which, okay, say that's, maybe I should do a dark color. Let's do like this. So my pi over 3 point is there. If I add 2 pi, I get this. If I subtract 2 pi, so n is -1, I get, well, oh, maybe not this one. Maybe I get this one. But, so I get this. Or no, do I still? No, I was right the first time. Okay. If I add or subtract 2 pi, I keep getting the other solutions. Then I go to my 2 pi over 3, which was here. And if I add 2 pi, I get this one. If I subtract 2 pi, I get that one. So I could add and subtract 2 pi as many times as I want to these two answers. And then I have all the solutions in the world, right? So basically the idea is that if we get a solution on a general, if we get a solution on like some interval, like 0 to 2 pi is typically what we're gonna do. Maybe it's something else, but it's gonna be on 0 to 2 pi. Well, like we see here, right? So so the solution on the interval 0 to 2 pi, this is going to be our, our solution like that we got here, right? And we would just list, oh boy, list these solutions. Yeah, we're home. So, sorry, everybody.
It's okay.
So I might let them
Put some
know.
reverb in there. It's like,
Let's get through this, right? Okay. Hey, wanna go outside? Go. Like they saw a squirrel or something. Like this is what's happening. Okay, so the solution on the interval 0 to 2 pi, this is going to be, we list these solutions, right? Because it's finite. And so maybe it's 1, maybe it's 2, maybe it's 4, who knows, right? But then we have what we're calling this general solution. And that's going to be, that's going to be what we saw here, right? And for those type of solutions, this is all solutions possible, like in the world, all of them. And for sine and cosine and actually, we'll see about if we even deal with tangent, but for sine and cosine, it's taking the solution on this interval and doing plus 2 pi n to all of them, right? So this is kind of how we can think of it. And then we write it as this nice, the nice general solution we see here. Okay. So now, we just saw this example of, we just did sine x is √3/2, right? But let's take a look at something a little bit complicated maybe. And okay, something happened here. This is a mistake, I think. Secant x. Yeah, like what happened here? I think this is a typo. So how exciting for us. Typo. Okay, what it should be is solve secant x equals negative square root 2. I think I copied and pasted secant x. That's what happened. But this is a typo, so we're happy. So secant x is negative square root of 2. And we want to solve it on the interval 0 to 2 pi, right? So first of all, I need to write this in terms of sine and cosine because I want to figure out where this is because secant doesn't tell me much. So if secant is negative, so remember, how do I want to say this? Secant x is 1 over cosine x. Or I'll say reciprocal. So what I think about here, if these are reciprocals of each other, if I have that secant x is negative square root 2, I'm going to make it over 1. This means I can just flip it to get cosine instead of doing like 1 over and then having to solve. So this means that cosine x is negative 1 over square root of 2. And then I can rationalize because that's what we do, right? Oops, yeah, that's right. So then I get negative square root 2 over 2. Okay, now I'm working with something good because I know that this is the pi over 4 intervals. Like it's either pi over 4, 2 pi over 4, 5 pi over one of the pi over 4s. But I want cosine to be negative. So remember, we have x and y. Cosine is the x. So at each of these points is root 2 over 2, right? All the fourths, the pi over 4s. But I want the negative ones. So that's going to be what I want where x is negative, right? So this is going to have negative root 2 over 2, well, for both of them. And then this one's going to have negative root 2 over 2 and then positive y. So I want these 2 points, which means I want these 2 angles. So the first angle is like if this was pi over 4, the dotted line, then this one's going to be 3 pi over 4. Then, you know, if we keep going, like it's pi over 4, I mean, this 4 pi over 4, and then we add another one. So it's 5 pi over 4. So the yellow is 5 pi over 4. And so these are our 2 angles that are going to work. So these are our solution, right? So I'll write this here. So 3 pi over 4, 5 pi over 4. And then if I wanted to write this in general, I don't think we do, but if I did, right, you would something like this: x such that x equals 3 pi over 4 plus 2 pi n, or x equals 5 pi. You would basically replace, let's see, you would take this and put it in place of this, and then you would take this one and put it in place of this one, right? So not too crazy. Excuse me. Okay. So the next problem we're going to solve. So again, and this is just, we are just solving, well, to start at least, they're asking just let's solve from 0 to 2 pi. Let's get comfortable solving this. And then writing the, once we can solve from 0 to 2 pi, writing the general answer is not a big deal, right? So let's do that. Okay. So if I want to solve, again, we're solving on the interval 0 to 2 pi. And I've got 8 cotangent 2x, whoa, minus 5 equals 3. Okay. This is good that I only see, so looking at this, I only see Okay, so looks like this is gonna happen all the time, I guess. Um, oh, a second. Okay. Yeah. So no idea what happened. It just all of a sudden I was talking and I looked up and Zoom just disconnected me. Yeah, lately my internet stays with me. It's Zoom. Like I think it's my Zoom license. Maybe, well, I told them I'm not teaching next semester. Maybe they're already kicking me out. So I apologize for this, but thank you for bearing with me. Okay, so we're back, and I mean, yeah. Now Colby. Oh, did it assign Colby as the? Everybody picked you as the teacher. Okay. Let me. I wonder if it's how I'm doing this, but whatever. Okay. So yeah, lucky you. Don't worry. If this happens again, I will just give me a moment back. Okay. So we're back. We can see this same thing, right? So I was saying we don't want to use the trig identity, like double angle, like form. We're just going to convert it to sine and cosine and then go from there, right? So what we do first is we want the cotangent all by itself. This whole like -5, the times 8, I don't know what the heck's going to happen. So we need to get this by itself. So first we will, all right, oh, this is working, but where's anyone see the pen stuff? Like, how do did I lose my mind or what's happening? Oh, there it is. Okay. All right, awesome. So I'm going to say add 5 to both sides. We'll get 8 cotangent 2x equals 8. Then divide sides by 8 so that these cancel and just cancel there. And then I get cotangent 2x equals 1. Okay, so now I'm in business, and cotangent of 2x equals 1. This tells us, so remember, just a little aside here, cotangent is the opposite of tangent, reciprocal of tangent. So it's cosine over sine, right? So what this means that cosine 2x over sine 2x equals 1. And then that means that cosine 2x equals sine 2x. Okay, so this is telling me cosine and sine, they have to be equal. So the only places that they're equal, if we think between 0 and 2 pi, right? The only places are the pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. These are the only places that are equal. So instead of doing a double angle and making this all confusing for ourselves, we just want these to be equal. So basically what we want is we want 2x to equal these angles, right? Well, okay, not all 4, I guess, because, well, yeah, yes, all 4. Okay. Because they're equal at all of these. So even when they're one and, oh, except when they're opposite, right? So, yeah, okay. So when they're opposite, this isn't just because, what am I saying? Like if one of them is positive and one of them is negative, this won't work, right? Because we'd get -1 instead of +1. That's what I mean. So technically, I guess, let me try to undo this. So technically we want it where I think here and here. So I'll, let me write that. So we want this angle, and then we want the big angle. But that's 2x, right? So what we do here is we say, we write a little equation. So we're going to say the answer is when 2x is equal to pi over 4, or, because this, remember, this was pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So we want 2x is either going to be pi over 4, or 2x is going to be 5 pi over 4, right? And technically, it's also, if we want the, well, we're not getting the general solution, but if we wanted the general solution, just to show you, and maybe there's more solutions inside 2 pi because we have 2x, technically, this is what it would be, right? Plus 2 pi n. So what we're going to do in order to figure out what x is, we're going to say, okay, let's divide this by 2 or multiply by 1/2. These are the same thing. Okay, these are the same thing. It's going to be easier to write times 1/2 over here, but that's what we're going to do. So to get our answers, this gets us our 2 answers. We get x equals, so pi over, we distribute this to both. Pi over 4 becomes pi over 8 plus 2 pi n becomes just pi n. So pi over 8 plus pi n, that's what we're looking at here for the first one. And then 5 pi over 4 becomes 5 pi over 8, again, plus pi n. Now, what you want to check, the reason I added this 2 pi n in here is because we're looking specifically between 0 and 2 pi. And I know if it was just x, it would be pi over 4 and 5 pi over 4 and we're done. But because it's 2x, there might be more solutions within 0 to 2 pi where this is true. And so that's what we're going to look at. So we're going to say, okay, so I know for sure if I start writing out my solution set, I know for sure pi over 8 and 5 pi over 8, because that's what we got right here and here. So I know for sure those are 2 answers, and maybe that's it. But what we have to check is that when I, let's suppose, let's suppose, so if n was 0, it would be pi over 8. If n was 1, this would be 9 pi over 8, okay? N was 2, so I'll write this. This is like n equals 0, n equals 1. And we don't do negative because, again, we're only looking between 0 and 2 pi, n equals 2. And I'll do the same thing for the top and the bottom. So if n is 2, pi over 8 plus 2 pi. Okay, so I'm writing this over here, plus 2 pi. This is like 16 pi over 8. So this is 17 pi over 8. Okay, this was like bubble scratch work in my head. Oh, sorry. I'm not looking at the chat, but let's look at it. I missed why you multiplied by 1/2. Okay, what I was saying when I did that was in order, so I had 2x on the left side and then an answer on the right. And I said, okay, I need to solve for x. So normally I would just divide by 2. I mean, that's what I would write. But in this case, just because of what we have on the right-hand side, it's easier to write times 1/2. Same thing as dividing by 2. But in this case, it's just easier because I could have written like all of this divided by 2, but that looks funky and it's a little bit hard to follow. Yeah, cool. Good question though. So now I have these, and what I could keep going. I could say when n is 3, but I'm going to stop. I stop here because 17 pi over 8 is bigger than 2 pi. So this is not in 0 to 2 pi because it's bigger. So now I know this answer is in 0 to 2 pi. So I'm going to include that in my final answers down here. And then I want to do the same exact thing for 5 pi over 8. Add pi to that, and that's 8, 9, 10, 11, 12. What's that? 13 pi over 8. And then add 2 pi. Well, clearly when we add 2 pi, I mean, I'm not even going to write what it is. It's too big. I don't care because I'm adding 2 pi and I only care about the answers between 0 and 2 pi. But this pi is less than 2 pi, so it's an answer. So now I add it to my 13 pi over 8. And these are my final answers here. So when you're given something that doesn't have just x, has like 2x, what you'll do is you'll pretend it's just x and solve and get the general. So we pretended it was x. General answers were the blue, right? So these were the general answers if it was just x. But then we set it equal to what it was, 2x, and then we solved for just x. So it does require a little bit more work, but it would be way more confusing if you tried to use an identity and rewrite this type of ball game of a problem. So part B, we have cosine of, I think this should be, this is fine. We have cosine of negative x over 2. Now, just to make life easier, and it's root 3 over 2. Just to make life easier, I'm going to say this is the same because remember, cosine is even or odd? Even. So this is the same as cosine x over 2 equals root 3 over 2. And I like to work with positive things better. So I'm going to work with x over 2. You don't need to do this, unnecessary, but in the end, you get positives anyways. So, or positive numbers for x because we're going 0 to 2 pi. So, yeah, so this works. Okay. Okay. I might have to, after this problem, I need to go check on my dogs because my cameras just said there's a person in the backyard, but like no one should be home. So it's either reading the dogs as a human or something's bad. Yeah, maybe I'm going to grab them right now. So just give me a moment. Okay. All right. Thank you. Okay, we're back in action. Who exactly? It was me, but who did that? Nice. Okay. So again, I'm using this positive one. Again, if you wanted to use negative, this is fine. Your answers would be the same, but maybe look slightly different. So let's take a look at what we've got here. If I think about where, if it's just cosine of x, I'm happy because root 3 over 2, I know that exists at a few different places, right? So it's where x is positive. So the root 3 over 2 is going to be the point here and the point here, right? So it's where x is positive. So it's here and here. It's not, even though we have root 3 over 2 over here, these are negative, so it's not going to be at these, right? So I know that if it was just x, this guy is pi over 6, and the other guy is, okay, I thought I lost it. The other guy is all the way around, almost to the end. This is 11 pi over 6. We usually don't use ones this big, but that's what this is, right? So, and if I want to write these points, it's root 3 over 2, 1/2, root 3 over 2, negative 1/2, just so you can see the whole picture here. So basically what I'm going to do is I'm going to take my, x over 2 that was in the problem, right? And I'm going to set it equal to pi over 6 plus 2 pi and 11 pi over 6 plus 2 pi n. Exactly what I just did before. So x over 2 equals pi over 6 plus 2 pi n, and x over 2 equals 11 pi over 6 plus 2 pi n. And then to solve this one's nice because we just multiply by 2. So we multiply the whole thing by 2 by 2. And so what happens is these cancel and I'm left with, so x equals 2 pi over 6. I'm simplifying this. This is pi over 3. 2 pi over 6 is pi over 3, okay? Plus 4 pi n. And then this is equals 22 pi over 6, which is, maybe I should simplify, just pi over 3 plus 4 pi n. And you don't need to simplify that one, and you'll see why, but I did. We have this. Now, what I did before was I said, okay, if I have n equals 0, n equals 1, n equals 2, like let's plug these in and see what happens. So for n equals 0, I get pi over 3 and I get 11 over 3. Now, before I even go on, I don't need to find n equals 1, n equals 2 because I'm adding 4 pi and I want my answers 0 and 2 pi. So I'm going to put like not between 0 and 2 pi, right? You don't have to find those, but you might think, oh, my answer is just these two, right? And maybe, but 11 pi over 3, how big is that? You need to check how big, oops. You need to check how big is this? And 11 pi over 3, is it bigger or smaller than 2 pi? So 2 pi in terms of thirds would be 6 pi over 3. 11 pi over 3 is way bigger, right? So too big. It's too big. It's actually not an answer. Our only answer in this case is pi. So there's only one solution in this particular problem. And I feel like I messed something up here, but maybe I didn't. Okay. And I don't mean in this, in the next problem, but everything looks okay for right now. Okay. So we're gonna try to power through this. You know what? All right, I apologize for all the dog delays tonight. So hopefully he's not too bad, or maybe I can go somewhere. This gets... does anyone know if it's better if I have my headphones in? Maybe. All right, we're gonna move. All right, you suck, Kobe. Okay. Let's... Okay. All right, a little bit better. except I don't know if you can still hear him, but I can still hear him. Okay, so for this next, so the last problem, we're done, one solution. For this next problem, now we're solving, again, we're still solving on this interval, 0 to 2 pi. And, but now we have something a little funky. We have this 2 sine squared plus 5 sine plus 3 equals 0. If you think of this as like 2x squared plus 5x plus 3 equals 0, we are going to factor. And maybe I should not say x because that's confusing. Maybe I should use like u, where u equals sine of x. So if it's hard to factor with just sine here, what you can do is you can think of this as u squared plus 5u plus 3. And you could do the quadratic formula for sure. Or you could kind of play guess and check and hope that this works out, right? So I would have 2u and u. And then we got to figure out, okay, how do I get 3? Well, 3 times 1. So it's either like 1 and 3 or the opposite, 3 and 1. And I think this one is the one that works. And then you want 5u in the middle. So, and they're all going to be plus, I think. Yeah. So again, this factoring thing takes practice. If you practice factoring, you try some extra problems and or like look up factoring examples and just practice. But now that I have this, I can actually rewrite this equation as 2 sine x plus 3 times sine x plus 1 equals 0. So now I can write each of these equations just like I would here. Like here, I would say 2u plus 3 equals 0 and u plus 1 equals 0, and I would solve, right? So we can do the same thing. So 2 sine of x plus 3 0 and sine of x plus 1 equals 0. So then I'm going to get, I'm kind of, well, oh, I forgot. I shouldn't skip steps. So I subtract 3 from both sides, and then I divide by 2. So I get 2 sine x equals -3. Then I divide by 2. So I get sine x equals -3/2. And here I get -1 on both sides. Sine x is -1. Okay, I know that this is possible. So I know, like, we'll figure that out where that is. But -3/2, this is the same thing as -1.5. Remember, the range for sine is -1 to 1. So this is out of range. -1 to 1 for sine. And so what that means is it can't possibly equal this. Okay, so this actually, this piece, it's almost like imaginary solution. Like, you know how if you get, x squared plus 1 equals 0, well, x squared cannot equal -1. Just that same way, sine cannot be -3/2. So this is not going to even get the solution. The only one we'll focus on is this, okay? So we want to figure out where is sine -1 between 0 and 2 pi. So let's see. Sine is the y, and it's -1, 0, -1, only at this point between 0 and 2 pi. So that's this angle, and that's 3 pi over 2. So this tells me x is 3 pi over 2. And there's only one solution to this. And it's 3 pi over 2. To this complicated looking equation, there's one nice solution, and we figured it out. So it's kind of cool. So part B also looks kind of confusing. However, we can do something really nice. So I have cosine x, right? So I can factor this out. We're not going to factor it the same way we did last time. We're just going to factor out the cosine x, and then we can solve. So let's do that. Give me a sec. So I'm going to say cosine x, and then what's left is tangent squared x minus 3 equals 0. And now I can treat this the same way that I treated it before, where I set this equal to 0, and then I set this equal to 0 separately, because those are its factors. So let's do that and let's solve. So cosine of x equals 0, and then tangent squared x minus 3 equals 0. So for cosine of x equals 0, we know, well, we know where it happens. So if I just do a little, 0 pi over 2 pi 3 pi over 2, we know it happens at pi over 2 and 3 pi over 2, right? So 0, 1, 0, negative 1. So this is when x equals pi over 2 and 3 pi over 2. But keep in mind that we also have a tangent in our equation, and we need to think, oh, tangent is undefined at certain places. So can this be a solution? And notice that for here and here, tangent of these points equals 1 over 0. And tangent here equals negative 1 over 0. So this is undefined, right? So these are undefined. And therefore, we'd say tan x is undefined at these points when cosine is 0, right? And so this gives no solution to our main equation. That was supposed to be a sad face, but it was kind of bad. That's still bad, but no solution. I mean, it's not a big deal, but you can't use that as a solution, right? Because tangent's undefined. And so even though it might work with cosine, because we have that tangent in our equation, we have to keep this in mind. It's kind of like if you have a square root in an equation and you get a negative answer and you have like square root of x somewhere. Well, this isn't going to work, right? You can't have that. You can't see. Okay. So now we're relying on this other one. So we're going to add 3 to both sides and hope that this gets us tan squared x equals 3, gets us some type of answer, right? So here we can say tangent of x is plus or minus the square root of 3. And I'm feeling good about this because this should get us an answer. And what this means, square root of 3 over 1, think of this as like over 1. This is the same thing, and you should know it comes from root 3 over 2 and 1/2. That's where these are coming from. So it's going to be plus or minus root 3 over 2 divided by 1/2. Well, okay, I shouldn't write the plus or minus there, but it's going to be like plus or minus these two things. So basically, it's the positive ones and the negative ones. So what's kind of cool about this is that, well, let's see, we want root 3 over 2 in the top. Oh, and this is, I might write a little note to myself. This is sine x over cosine x. So we want y. I'm just trying to find where these points are. So this, it's going to be here, it's going to be here, it's going to be here. Oops, it's going to be here. Okay. And I'll write these, maybe I'll write these in like reddish. Okay. So this point is 1/2 root 3 over 2. This one is negative 1/2 root 3 over 2, right? This one is negative 1/2 negative root 3 over 2. And this one is 1/2 negative root 3 over 2. Now, all of these, the crazy thing is all of these are solutions because it could equal plus or minus square root of 3. So each of these, when I divide the twos, I mean, these twos cancel out. So when I divide, I could have positive over positive, positive over negative, negative over positive, whichever, negative over negative, right? I can have all of them. So the cool thing, I guess, is that each of these so let's do this. The first one, then the second one, then the third one, and then the last one. So this, for some reason, makes me think of Skittles, Taste the Rainbow or something, and makes me hungry. Even though I like just house dinner before this. Okay, so we need to figure out, okay, what are these angles? I have not written these in here yet. And I meant to write. So this first one is pi over 3, and then we're just adding, so it's 2 pi over 3, then 5 pi over 3, then 7 pi over 3. So my solution is going to be all the pi's over 3's in our unit circle. And I didn't mean 7 pi, that was too much. 5 pi over 3 is plenty. And remember, we still have to stay in 0 to 2 pi, but these do that, all 4 of these. Okay, so any questions about this so far? Do we need to include the other 2? Did I miss 2? Which 2 did I miss? Pi over 2. Oh, no. So I explained we don't include these because when I plug that into my regular equation, tangent is undefined there. So although we got that those are solutions, they're not solutions to this particular equation, like the main equation from the beginning, because we have this tangent. And if I plug in pi over 2 to tangent, I get undefined. So that's a really good point. We do not include those. Even though we got them, we do not include them in our final answer. Yeah, thank you for asking.
I have a question.
Yeah, Veronica, go
When
ahead.
you're using tangent with the square root of 3, is it just a given that you're going to use square root of 3 over 2 and then 1/2?
Yes.
Okay.
Yes. So, and if you had cotangent of like root 3 over 3, that means like, so, okay, bear with me here, but if it was cotangent and it was like root 3 over 3, this is a given that this was probably 1 over square root of 3, which means that tangent was square root of 3. And then it was square root of 3 over 2 over 1/2, right?
Okay.
So yeah, that's basically, I mean, I wonder if you put this in a calculator, I don't know that it would probably give you the decimal, but then you could check. So you could say like, inverse tangent of root 3, and it would probably give you, actually, if it was degree mode, it would give you like 30 or 1 equivalent. So if you were in degree mode, you could do like, and you weren't sure, you could put in your calculator something like this inverse of square root 3 or negative, plus or minus, whichever. And this should get you, in degree mode, it'll get you 60, right?
Okay.
And then you could say, oh, if it's at 60, that's got to be its root 3 over 2 and the 1/2, and yeah, and it's not all the other ones, right? So just so you know,
Yeah,
the calculator can be our friend.
There were some homework problems that had tangent square root of 3, and I just could not figure it out. So,
Yep. So this and granted, I mean, I can check your test, but I doubt we put tricky ones on your test. But that the homework is going to load up on the tricky
Okay.
ones. Yeah.
thank you.
Even when I see like secant, like in this other a while back, I saw secant is 2. Okay, maybe it was at like maybe it wasn't even. All right, maybe I'm making things up.
Might have been the one that had the typo, maybe.
Oh, it was the typo one. So you're right. Thank you. Wherever I wrote that. Okay, it was this one. So when I see secant with the square root of 2, I know it's involving root 2 over 2.
Okay.
And if I saw cosecant with that, same thing. So yeah, so there's little tricks that are good to know, but you can also have your calculator help you out and try to figure out what angle that is.
Okay. Thank you.
Yeah, good question. Okay, so let's take a look. Now, again, we're still solving on the interval 0 to 2 pi, but I have another. So, okay, if I let u be sine of x, oh no, I can't. Oh, just kidding. Okay, because this is, this is different. Okay, so I see, so what I was doing to start is what I would think to do, but then I saw sine and cosine. So it's not too bad because all we have to do is change. We know, remember, sine squared plus cosine squared is 1. And so if I want to replace this, oh, why does it keep doing this? Let's undo. Okay. So if I want to replace, this sine squared to get cosine, I would just subtract the cosine over, right? So I would just move this over to this side, right? And so let's do that. So I'm going to say 1 minus cosine squared x minus 5 cosine x plus 5 equals 0. And then I'm just going to simplify this. So distribute the 2. I get 2 minus, I already messed up. 2 minus 2 cosine squared x minus 5 cosine x plus 5 equals 0. And then what I'm going to do here, well, first I'll combine like terms. So the 2 and the 5, I can combine them, right? So I get negative 2 cosine squared x minus 5 cosine x plus 7 equals 0. Now, in order to factor this, I want the first term, like now we can say, okay, now we can let u equal cosine x. But I want this first term to be positive. I don't want a negative number because factoring, you always want your first term. You really don't want even a coefficient, but that's fine. But you want a positive. So what we can do is I'll write a little note, factor out -1. And so what that looks like, and I'll write it here, is negative times 2 cosine squared x plus 5 cosine x minus 7 equals 0. So I factored out this -1. And then because the other side equals 0, and you can see I changed, when I factored it out, these minuses changed to plus, and this plus changed to a minus. And then what I do is I just divide everything by -1, divide by -1. It doesn't change the right-hand side, right? Because just 0, and it gets rid of these. And it's the same problem. But the nice thing is that now I have positive 2 cosine squared x plus 5 cosine x minus 7 equals 0. Now I can go here and factor, because it's 2u squared plus 5u minus 7. So again, for this, you can do the quadratic formula and be brave, right? Or I'm just gonna do guess and check. I know it has to be 2u and u. That has to be what it is. And then it's either 1 and 7, right? Or again, or it's 7 and 1. And maybe I have to mess around with it, right? So maybe I start with the 1 and 7 and I learn, okay, one of them also has to be positive and one has to be negative. I don't know. But maybe I get plus u. So like if I distributed this, I'd get 2u squared plus u minus 14u minus 7. Okay, this middle term gives me negative 13u. This is not, and what I want is 5u. So this is not right. Okay, so I would erase and try again. So I'd say, oh, maybe switch the 1 and the 7, right? So maybe 7 here, 1 here. And eventually, I mean, my guess and check method is going to work, right? Because there's only so many options. Worst case is that you multiply it all out like 2 or 3 times and then you get the answer. But this is actually going to work because I get 2u squared minus 2u plus 7u minus 7. And this middle gets us, right, 5u that we want. So great. So this works. So that means that I can go back to my problem and I can fill this in with cosine of x. So 2 cosine of x plus times of x minus 1 equals 0. And then I do exactly what I did before. So I have 2 cosine x plus 7 equals 0, which I'll subtract 7. Okay, and I'm kind of running out of space here. So I'm just going to say 2 cosine x. Actually, I'm not. I'm also going to say divide by 2. So divide by 2. So I cosine x equals 7/2. But what's happening here, again, this is out of range. It's bigger. Negative 7/2 is like negative 3.5, right? That's way too big. Cosine can only be negative 1 to 1. So this, oh yeah, and Jakob, sorry, I just saw your chat. Jakob is correct. This gives no solution. So no solution for this part, but we still have this part, right? So there's still hope. So now I say cosine x minus 1 equals 0. So cosine x equals 1. This I can get with, right? I know that the cosine of x is 1 at this point. So 0. Okay, so at this point here, this is 1, 0. That is where cosine of x is 1, and this is x equals 0, right? So my answer, so that's the drawing here, and my answer is just 0. Which is pretty neat because this solution that we got is the solution to our original equation. I mean, it works for the new equation, but it works for this crazy looking weird original equation. But we just rewrote it to be nice so that we could factor and solve. Yeah, no worries, Joseph. Okay, yeah, oh yeah, because Joseph always supplies all the goods from class. I will be sure to post notes right after class, and yeah, hopefully other people can, help out. But have a good night, Joseph.
So is 2 pi not